10 years ago, some strange coding methodology of putting all the complexity in the decoder. It's not about that. We're going to talk about network distributed. So we try to distribute the encoding further down the pipeline, and I'll give you some solutions of how we do it. I'm from Ghent University and IMEC. IMEC is a research institute. So everything you will see here is, let's say, thinking forward. So we will not be able to implement this today. Try to think a little bit without all your boundaries you have today. And yeah, try to go with me. I would like feedback as well. So if you have practical issues or problems you see in the future, please go ahead. I wanted to show you, I wanted to brag with how nice Ghent is, but yeah, we're in London, so yeah, nothing to compare to. As a researcher, we have looked at, let's say, video on demand, video with a lot of latency, and let's say, problem solved, we get nice quality. We won't consider it today. Then go a step further, low latency, you want to interact with people. And in this scenario, you have a one-to-one communication. You have one specific encoder communicating with a specific decoder, one-on-one. There's communication back, feedback. So we consider that solved as well. You can do a lot of things, but since you have one encoder for each receiver, not enough challenge, let's say. Let's go one step further. One-to-many, live broadcasting, low latency. And I heard some interest already today in very low latency. So that's the direction we will go today. We'll go lower and lower latency. As an example, watching live games, you already heard. If your game is getting in too late, it's quite boring to hear everybody cheer. One step more challenging, if you have, let's say, a class being distributed to people and they want to have the opportunity to ask questions, to give feedback, to really get into a conversation. So a one-to-many scenario at a low latency, it's quite challenging, and we would like to present to you our technology to do this. What do we have today? Something sort of adaptive streaming, let's call it like that, on an abstract level. So what do we do after streaming? You know, we encode at different bit rates. We segment the video. We encode it at different bit rates, and then everybody's client is requesting a specific bit rate. One thing that is a pity in this scenario, let's say we have a person with a 6.5 megabit connection. He will be dropped to a 5 megabit. So there's 1 megabit left doing nothing, which is actually a pity if it's really necessary. These are not, let's say, practical bit rates. Just for your information, there's no service that only starts at 2 megabit. But other second issue, segments start with iframes in general, let's say. So if everybody is receiving these iframes, the goal of an iframe is to switch layers, is to, let's say in a low latency scenario, to recover from packet losses. In this case, when people have a constant bit rate, they will get all these iframes, get bothered with all these iframes they actually shouldn't get. So these are the issues. What is the solution for this problem? I'll first, before going to the solution, I'll dig a little deeper to get you, let's say, on the same, same terminology. A lot of technical people here, but if you didn't know, a video stream is divided in two parts, let's say, mixed together. But you have the coding information. These are the block sizes. So the video is divided in blocks. So the fact that you communicate what the block size is, what the motion vectors are, what the prediction direction is, all of that information, let's call that the coding information. And then you have the residual. So when you do predictions, you make an error, and you have to put in residual information. That's the one you transform, quantize. So let's call that the residual information. And we don't dig deeper than that. So Just remember, video stream, 2 parts, coding info and residual. So if we represent adaptive streaming, like schematically in blocks, you have a segment, it starts with an iframe, you have a lot of other frames behind it, a new segment, an iframe again, a lot of other frames. You have the different resolution, the different bit rates, and then the end client, the end user client, will choose a segment. For a next segment, choose another bit rate and go on. In this case, all these segments contain coding information represented by the block and the residual represented by the contents. This just to introduce, I'll use this diagram again for following technologies. So what would we ideally want to do? So personalized transcoding or encoding, what we actually want to do is give everyone a personal video stream. Every connection is personal. Your way of walking wirelessly, your connection is personal. You have packet losses. You don't want to bother other people with iframes when you have packet losses. If you have a good connection, you don't want to bother with others' iframes. So what do you want to do? Have the video encoded for everybody separately. So every individual has his own encoder, has his own bitrate, his own set of iframes. Problem, of course, why don't we do this? It's a lot of encodes. It's, let's say, too much. We can't do this in practice, so we need a solution. How does this look? We have one basic representation. Let's say we have a high quality 10, 15 megabit video stream. We transmit it over the cloud towards the cloud edge, and there we have a transcoder. We decode it, small complexity, that's why I drew it small. And then we have an encoder, which is big, a lot of complexity, but everybody has his own encoder. So at some point you have a certain resolution, you can switch, you can introduce iframes, you can change it whatever you want. If somebody's bandwidth drops, you drop it for him because he has an individual encoder. If a frame is lost, no problem, you communicate it back. The encoder will know it, will remove it from his reference list, and there will not be any drift. Errors will be corrected as soon as the information is communicated forth and back. So ideal solution, but complexity, big issue. We can't do this. So we thought, let's investigate complexity reduction. It's also what a lot of people do. Yeah, this is just schematically how it would look. So as I told, you send a big video stream over the cloud. At the edge, you transcode it, and then on the last mile, wireless connect 4G or whatever DSL connection you send the personal video stream. And this is what, let's say in MPEG terms, what was tried to put forward as under the project of network distributed video coding. Just the general concept that you don't do all the encoding at one point and then start to distribute it, but at several points in the network or at one point here at the edge, you can start to transcode and give a personal video. Just for the record, we didn't gather enough momentum, enough companies to follow in this. I think it's too early or too ambitious, but who knows. So let's say reducing the complexity of a transcoder or an encoder. This is the ballpark we are playing in. So this is a graph showing speed up. In this case, it's compared to the HEVC reference encoder. So consider the speed up with a grain of salt. And then on the vertical axis, there's BD rate, which is the Beyond-the-Guard delta bit rate, which actually means how much percent in overhead do you pay in bits. So for the same quality, how much more bit rate do you need to send? Because in the end, if you speed up an encoder or a transcoder, with every step you speed up, it's an evaluation that's done less. So if normally you would check all intra-directions, and in this case you only check half of them, you get a speed up, but you will get a drop in quality or an increase in bitrate. And that's, in this case, at a constant quality, this is the increase in bitrate. So what you see here is that most research is in the ballpark of speed ups up to 10. So 10 times, 10%, no, 10 times faster, sorry, 10 times faster. And then here, let's say an overhead around 5–6%. And that's like the ballpark they're playing in. If you get faster, you have more overhead. To be honest, nobody tries to go any further here, because then your BD rates would get too high and papers won't get accepted. So that's just like an academic issue. So what we did with personalized video adaptation is the following. So you see these 3 points in the back. So here, these 3 points, let's say a speed up of 120 times faster. In HM, it's rubbish. HM is so complex that, let's say, 120 times, it just corresponds with the complexity of a decoder. So we don't do any evaluations anymore. We don't check different block sizes. We don't check different intra-directions. We just apply one. And we will say which one you have to apply. So don't consider the speed up as a real number. Just think of it as being an encoder at the equal complexity of a decoder. Not thinking, just getting commands of use block size 64 by 64, use this intra-direction, and now close the loop and do some intra. So what we see is we end up with 10% overhead, 13, almost 20. And then there's this huge gap in between. And this huge gap is empty, because actually, if you, let's say, what happens here is people do machine learning. So what they do is they get a ground truth of what they have to do in a video encoder, and they try to predict it in a transcoder with information that's coming in. So let's say a video stream of 5 megabits comes in, and you want to make it into a 1 megabit stream. You look at the block sizes. If you see the block sizes are small, you probably need small block sizes as well, or maybe increase them a little bit because you're reducing bitrate. And that's, with machine learning, you can train that. The problem is, the moment you go further and further, you can predict more and more information, it's no problem. But the overhead will shoot up and go like in a straight line. If you see like this line, it will go on like that. And you won't get really far. That's what the problem is. At some point, you can't speed up the encoder anymore. If you speed up the encoder more, your bitrate will increase so much. And that's what I would call the fragility of a video stream. So a video stream is a serial process. And the moment you change something in that video stream, the bitrate will blow up in such an amount that it's not useful anymore. And you can put on any machine learning technique that you want, you won't get a result that's good enough because the video stream is fragile, let's say. We tested it on several videos. Let's say, copy the entire video, all the block structures, everything else, but change one intra-direction and leave everything else unchanged. And then, because, let's say, the KBAC, the entropy encoding, has like different predictions, the bit stream will blow up 5–6%. Just to show, like, a video stream is fragile. The moment you touch it, you get overheads, which are big. And that's why with pure copies, you won't have that. So what do? We copy the coding structure. So as I told, every frame is divided in blocks, motion vectors, intra-directions. We leave that information as is. The only thing we change is the residual. So imagine this is a 5 megabit per second, one of the images of 5 megabits per second. What do? Instead of putting all this residual into it, we put less residual into it, and it becomes a 4 megabit per second video stream. So do you see? We keep the block sizes, the motion vectors. We don't recalculate them again. We just keep them as is, but then put in another residual, a smaller residual. We quantize more, and with that we reduce the bitrate. So in general, if you see, a video stream is almost, let's say, 50% coding information, 50% residual. So from a 5 megabits per second video stream, we can make a 4, a 3, but not a 2 megabit, because there is already 2.5 megabit of coding info and only 2.5 megabit of residual left. So we can't keep on reducing. We have like a ballpark, a range in which we can play. So how does this thing, what does it look like? So what we do is, again, we send this high quality video stream to the cloud edge. We have all these representations of certain bit rates, let's say 5 megabit, 3 megabit, 1. But we only keep the coding information and not the residual. So the residual we throw away, we're not interested in that anymore. We only say this is the block sizes, the motion vectors, the intra-directions of a 5 megabit video stream. And this is the block sizes, blah, 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 of the 2 megabit bit stream, and so on. What do we do in the personalized transcoder? We decode, and instead of encoding, we tell the encoder what to do. So if this encoder has to output 5 megabit, that's easy, because it takes the 5 megabit video stream, the 5 megabit, we call it a control stream or a side stream or something like that. So this side stream with the block sizes, it tells this encoder which block size to use. So if it wants a 5 megabit output, it takes block size 64 by 64, whatever is in there, applies it, and only closes the loop by calculating the residual and putting the residual in the video stream. You would say, oh, for 5 megabits, it's a waste of time because you already calculated it here. But this stream could also be used for 4 megabits or 6 megabits. So also for 6 megabits, let's say, we take the 5 megabit block sizes, motion vectors, we apply them, we just add more residual. And just by throwing in more residual in the video stream, you get a 6 megabit video stream. And with that thing, imagine, these are iframes, these are p-frames, these are higher resolution p-frames, higher bitrate p-frames. What can you do? So this personalized encoder, at the complexity of a decoder, can serve its end user at any moment in time. If the end user has a problem, drop the packet, it can feed it back, and this one can pick an iframe here, insert it, use the block sizes it gets, insert residual information, output, and go on. And then the next frame is a p frame. It just picks a p frame of whatever bit rate you want to choose, picks that block information, uses it, don't have to calculate it, insert residual, closes the loop, so whatever frames you had before, you can still close the loop, and that's the only thing this thing has to do. Closing the loop, like doing the prediction, getting the residual, and put the residual in the entropy coder. You can compare it a little bit with how with HTTP websites are packaged, let's say zipped and put together and then transmitted. It's a little bit the same. We just zip all this information, we KBAC it, we entropy encode it together, we close the loop, and then we output the video stream. So this is the let's say the curve, the performance curve of what you get when you do this. So I already saw people frowning and looking like, what, you're going to take block sizes for a 5 megabit video stream and make it 6 megabit by putting 1 megabit more of residual into it? Probably not that good. But here is the result of it. So the A, B, C, and D, these are traditional adaptive streaming, let's say, recipes of a bitrate ladder. The dotted line, the dashed line, is the one you would get with adaptive streaming. So a person, let's say, with 3 megabits, he will end up, yeah, it's a bad example actually. Sorry, a person with 2 megabit, he will only get, so 2 megabit, he will only get here 1 point something. This is lost, what a pity. He had 2 megabit, he has to leave open 800 kilobit, and he gets this quality here, PSNR. Let's assume PSNR is quality. Yeah, so he gets this quality, which is a pity because with 2 megabit, he could have gotten, in ideal case, something around here, this quality. And this is what we offer. So the triangles represent the same block size, motion vector, intra-direction as point C, but with less residual, and then you end up in the triangle. So nicely, this person wins, let's say, this quality just by filling up his line. So if this person has 2 megabits or 3, we give him 3 megabits. So the same scenario here. We had a 5 megabit, let's say, starting point. If we put in less residual, you get the blocks. You end up where the blocks are. So depending on what delta QP you apply for the residual, you end up in one of these blocks, and you see all of these blocks provide a higher quality than the adaptive streaming counterpart, and that higher quality is given by filling up the line full of bandwidth that you can provide. So how does this thing, what does it look like? So in the back end, over the cloud, you send your high quality video stream, you send all your side stream, control streams, whatever you want to call them, with only the block information and the motion vectors. The only thing these things on the cloud edge need to do is decode the high quality one and encode it again, but the encoder is as the same complexity as a decoder. It just applies block sizes, motion vectors, as if it was a decoder. So what do we give people? Everyone a personal encoder at a complexity of 1 point something decoders, depending with how many people they share this infrastructure. But so let's say worst case, people will have 2 decoders just to supply them with their video. And in this way, it may look expensive now, but yeah, we'll never know what the future gives if, let's say, cloud edge computing becomes more and more popular, and the rates of doing that become less and less. And maybe for, let's say, a high-quality service, a paid service, this starts to make sense. But yeah, I would like to hear your opinions, of course. So thank you. If you have any questions, please go ahead.
I saw a hand raise here. I have my own microphone. Here you go.
Thank you. Very interesting idea, I think. One question in terms of the experience, if you're able to tweak the bandwidth given to the user on one individual frame basis, you know, being able to jump, being able to be between 2 steps of the ladder, what is the experience like for the end user? Is it progressive enough? Is it granular enough so that they don't see the changes? How does that look?
But they don't step on a ladder, actually. They so this is the old ladder. So there you jump. So with the old system with 4 recipes on the entire bitrate scale, you jump from 500 kilobit to 1 megabit to 2 point something megabit. In our case, you don't. So you switch from 500 kilobit to 600 kilobit to 700 kilobit. So you can, with every frame, you can step on, you can jump, you can go wherever you want on this entire line. Every dot can be covered, so your steps will be smaller. And the additional point is with normal adaptive streaming, you need an iframe for every jump you make. So every iframe is like a small flicker, definitely in the smaller bit rates. So every time you jump from one point to the other, you show a flicker. We don't. So we don't send any iframe if you don't need one. If you have a good connection that doesn't drop packets, we just send you these intermediate points. And then if you switch, imagine a P frame predicting from the previous frame, which goes up in quality. So your quality will always go smooth up, like let's say with iPictures, you have a CRA and an IDR. If you know the difference, like a CRA is OpenGOP. It's the same with an OpenGOP iframe. You build up to the iframe, most of the time lower in quality if you do low latency, so every iframe is of lower quality. But if you open the GOP, you will see like the quality dropping to the iframe and then building up again. So you have to consider it more in that way. It will be way more fluent. The only problem that could be is that the bandwidth of a certain person switches erratically or drops at a lot of points. But then I think there is no solution. If you want low latency and you don't want to buffer and the bandwidth is going crazy all the time, what can you do except like buffering? So yeah, I think it will look better.
Hiya. Have you done any tests against, because you're keeping the same block sizes, like, obviously, but you might make different block size decisions depending on what rate you're aiming at. So you might want to like bias towards larger blocks for a lower rate or something like that. Have you done any testing against like encoder decisions where block size might vary on different rates compared to just boosting the residual or giving less bits to the residual?
But that's always the case. So let's say if you go from A to B, your block sizes will decrease. If you go from B to C, they will decrease more, and at point D, they will be so small because you have the rate to have small sizes. So that's in our case the same. So B has, let's say, smaller block sizes than A if you keep the same resolution. But let's say in our case, we just keep those block sizes. So for the red dots, we apply all the structure of A, so we don't change any block size, because that's what we observed. Like if we change any block size of all of this, even one, you already have a bit rate loss of 5%, so you don't want to touch the video, the block structure at all, only the residual. But does that match what you wanted to hear?
Kinda. I assume you need to very specifically choose which rates and sizes you pick to be your base.
Yeah, indeed. And the more you take of these, the better it will be, because let's say the further away you get from this point, imagine that B and let's say B and C are gone. If you only chose A and D, the further you go from D, this curve comes to do goes like this. So your loss gets bigger and bigger, and the same goes from this point. So the more points you can fully encode on this bitrate ladder, the better it works. And from our measurements, we came up, let's say, if you have a good trade-off, was like 6 points on this ladder. Because if you add more points, you'll see like here, they getting closer and closer to each other. Your added gain becomes smaller and smaller, but it all depends on what's the cost of your encodings, what's the size of your bitrate ladder. It all depends on that.
Anyone else? Any more for Emil? Set.
Earlier today, during the panel discussion, Derek referred to Alex's talk in Demuxed, where you could reuse data from your multi-rate encoder. And it looks to me there is like a lot of similarity between what Alex was proposing and what you're saying. In Alex's cases, he would, for example, encode D and then use that information to predict stuff in C, and maybe it's using machine learning or whatever, or it's just using the same information. In your case, you have like A, B, C, and D encoded separately. But if you looked into LibX265 and the interface for reusing information from all your separate waypoints to encode your individual encoded streams, and then if you have done so, what do you think about that file format, and how would that relate to your MPEG activities, future MPEG activities?
Well, they, let's say, to make the analogy, the file format that would come out of H.265 and that X.265 and that you would put in again, that's this part. So that's, let's say, similar, but we wouldn't go for whatever. I think the most efficient way to handle this data is just throw it through the Kabak encoder like we do at the moment. It has been optimized for this information, so it would be strange to take another file format to do it. But with respect to the comment of the machine learning, so it's the same for multi-rate encoders. So people say like, oh, video stream 2 megabit looks like 5 megabit. So let's output all the coding information, do machine learning, and encode the 5 megabit faster. That's this issue. You will come across the same issue. It's, let's say, the same problem that you have. If you want to make a fast simultaneous encoder, you will play in this ballpark of 10 times speed up. The moment you go up, you'll see those overheads, so the bit rate that you lose from your faster encoder, you will see them go up, and at some point you will go over, let's say, our baseline of copying everything. So I would say to people, make a nice machine learner, make a fast, let's say, multi-rate encoder, but be aware, the moment you cross the point of just copying all the block sizes and don't do any machine learning and just copying whatever is there, this point should be your upper limit. If you're doing worse than that, then don't consider machine learning and just copy the thing. And that's what we learned from this big gap. Yeah, there's nothing useful in between. There's like high overheads and no speed up, so be cautious with what you do.
Anyone else? I actually have an observation / question again, kind of parodying back to some stuff that was at Demux and the Sydney Video Meetup last month. Michelle Munson's new startup is a programmatic blockchain video startup where the concept is that all of this sort of stuff happens, but it happens on a programmable blockchain. So you can leverage blockchain to do your encoding. Yes, buzzword bingo, etc. You leverage blockchain to do your distributed video encoding, and then obviously you just pull those segments on whichever client is pulling them. Could this be applied in that way elegantly?
Well, I don't see it, and I'll have to look into it because, yeah, it's like machine learning. People talk about blockchain a lot.
Oh yes.
That's why I also wanted to scope this. I don't see any reason to do this for video on demand or one-to-one video encoding, low latency. I only see a reason to do this in one-to-many low latency video encoding, and in that case, putting this thing in a blockchain that takes 10 minutes to validate. I don't see how it works. So,
to be clear, I agree with you. But
okay.
Anyone else want to ask anything? Last chance. All remaining questions shall be taken at the pub. Uh-oh.
So when you say edge cloud, how close towards the client device are you talking?
Let's say when we do research, let's say we try to be agnostic to where companies would put it or whatever they do with it. For me personally, I think that the nicest thing would be to put it as close as possible. Let's say if here's a 4G or a 5G tower, let's put it there and try to do the processing there. It would be nice, but then people come with practical issues. We don't bother too much about as academics because you have to hand over and people are moving and you have to move those processing to the other part. And so I think it depends on the application, but purely from a scientific point of view, I would say push it as close as possible, that you get like one easy personal line that's very low latency, and if you have a latency, let's say, of the last wireless connection or the last DSL connection, it will be so small that whatever packet loss you have, people won't see it because the next frame you already, or the next half frame, you already have a solution pushed through. Removed it from your reference buffers, or in worst case, introduced an iframe and nobody will notice any loss at all. Let's say that's the thing about it. Practically where to put it, I can't make any statement.
Okay, sorry. I know that was a harsh question.
Okay. Thank you.